Problem 715 gives a whole bunch of data on a cylindrical test specimen. Refers to it as stainless steel, and it has a diameter of 0.505 inches. So we'll use all of the US units in this particular problem. It's got a gauge length of 2 inches and it's pulled in tension. So we will, instead of drawing it, we'll use a spreadsheet, and we will use, again, just the US units. So just take this, put it here, and that. Okay. Now we need to, instead of using load and deflection, we need to calculate the stress and the strain. So in order to do that, we need to first find the area to find the stress. So the original area will equal diameter. Let's put the diameter in here. Okay, and is 0.505 inches. That means our area is going to equal this squared, but we need to make sure it's in parentheses, multiply by pi, divide by 4. And we'll name that A0, so we can always use that in our calculations. Okay, so our stress will always be equal to the load divided by A0. And we can just drag that down, and let's make it a little more consistent. We don't need decimal places. And number 0 decimal places. And the stress is going to be in pounds per square inch. And then our deflection, oops, we'll need to calculate deflection. So it's easier to do this. Put our deflection in inches. That will simply be equal to our total length minus our original length. We'll call it L0, but we haven't made a name for it yet. So we'll take our original length, which is 2, call it L0, and now makes a lot more sense. We'll drag down and format these cells as well, and we'll make them 3 decimal places. Now we can calculate our strain. So our strain will be in inches per inch, which is in effect unitless. So, I never did that. So can just drag this up, and this should be 0. There we go. So our strain is equal to our deflection divided by our original length, and that's what it looks like. So we're going to format these cells and make them 4 decimal places consistently. Now we are ready to make our stress strain diagram. Okay, go to insert a scatter plot, and with straight lines, and oh dear, this does not look like what we wanted. We want to switch the row and the column. The easiest way to do this is to undo and switch the columns. Now go to insert scatter plot, straight lines. That's more like it. Okay. So then let's modify this chart, and okay, so label that properly. Don't need this. There we go. Go to the axis title, and this axis is stress in PSI, and this should be strain, and there are no units. And we can dispense with the legend there. Might want to put inches per inches just in case someone thought we had forgotten our units there. Inches per inch. Alright, now that is the first step. We need to plot the data as engineering stress versus engineering strain. That is done. Next, part B is compute the modulus of elasticity. The modulus of elasticity is applicable only in this region, which is the elastic region. And the best way to find that is by checking when it actually starts changing. We will estimate the modulus of elasticity for every point. So this is going to be the change in stress over the change in strain. So here's stress minus here divided by the change in strain. This minus this. And this is also going to be in PSI. But let's drag down and see when it really starts changing. So we are at 28 million, 28 and a half, 28 and a half, 28 and a, close to and a half, close to, oh, this looks like the point at which things started changing. So let's estimate our modulus of elasticity as the difference here to the very beginning. So equals the change in stress minus that divided by this, because both of them started off at 0. Okay, so we have an define our E modulus of elasticity as about 28.5 million psi. So that is step B. Now, determine the yield strength at a strain offset of 0.002. This is what's meant by the 0.2% offset. If we look really carefully at this part of the graph, we'll see it has this nice straight line feature given by the elastic region. If we shift over to 1/10 of this 0.02, so it would be at 0.002, and we draw a line that's parallel, we will run into this curve somewhere up here, and that will be the rule of thumb 0.2% offset. So we can insert a shape, in this case just a line, and we're going to make this line as parallel as we possibly can here. Now we can zoom in even if we want to. So we're going to make this line nice and parallel to the other line. And then move it over. Okay, that's about 1/10 of the way. You see what runs into this part of the chart? Okay, so that is part C. Part C is 0.2% offset yield psi. And that's about 112,000. Okay. Next is the tensile strength, and that is found on the graph, the very uppermost point. So we see it's about almost exactly 180,000. So $180,000. Okay, part E, the ductility, is the plastic strain at fracture. So here we are. Plastic strain is 0.115. That's in inches per inch. But it is equal to this strain minus the strain where we had of the elastic region. So we're going to subtract the strain that is here at the very uppermost end of the elastic region, and end up with 0.112. But this is usually done in terms of percent. So let's go to 1% there. So it's 11.2%. Finally, we need to calculate the modulus of resilience. So and this is also going to be in PSI. The modulus of resilience is equal to the square of the yield stress, and we'll use the offset yield in this case. So square that, and then divide by twice the modulus of elasticity, and that ends up to be 220 psi. This problem looked at a variety of different factors in a test situation, and we were able to calculate from the load and the length, deflection, strain, stress, estimate the modulus of elasticity, see how it changed and was only applicable in the elastic region, and make a good estimate of what it is. Then calculate the, or at least estimate the 0.2% offset yield. Then look at the tensile strength, be able to see that. That was just by observation. The ductility we calculated as simply the final ductility minus the ductility at the end of the elastic range. And finally the modulus of resilience using the equation 714 from the Callister textbook.